Hello everybody! In this video we're going to continue our discussion of the topology of the real numbers, and we're going to talk in this video specifically about closed sets. So you might be guessing, since we just did a video on open sets, that a closed set is just a set that's not open, which from an English language point of view would make a lot of sense, but mathematically it turns out is dead wrong. So uh, yeah, we're going to have to give a precise definition of closed, and it's not going to be just not open. So in order to give that definition, I first am going to define what are called boundary points. So a boundary point of some subset S of the real numbers, so here we'll have some subset S, is a point X, so some real number. Okay, we're not claiming it's in S or not in S at all. We're just saying at some point, such that every X coin, okay, so every X-centered open interval, intersects the set S and S complement. Okay, so that means you write down any X coin you like, and that X coin is going to contain some element of S and some element not in S. Okay? Now, based on our notation for interior point, it would make sense to call the set of boundary points B of S, but in mathematics, they have a pretty standard symbol to talk about the boundary of a set, and it's a little bit confusing here. So the set of all boundary points of S, right, which is going to be called the boundary of S, is denoted, and we're going to use, oh my goodness, it's the partial derivative symbol. All right, so in LaTeX, that's backslash partial, okay? But this is what in math we're going to use for the boundary of a set S. Okay, and so now we can give a definition of what it means for a set to be closed. So the set S is closed if S contains all of its boundary points. Okay, so it will definitely help to have an example here. So let's consider the interval 1 to 3. So I have 1, I have 3, and I get to include the endpoints. So I want to know what are the boundary points of this set. Okay, so I'll put a little partial symbol in front, so I'm asking what are the boundary points. So if I take something from the interior and I put a coin around it, right? So maybe this is my X, and I make a little X coin, you can see that this X coin is completely contained inside 1, 3, so it intersects the interval 1, 3, but it doesn't have any point outside. Right? Now I could have made it much bigger so that it did, but the point about boundaries is that every X coin is supposed to have points both inside and outside. So something which is in the interior is not going to be a boundary point. On the other hand, if I take something in the exterior of the set, I can also put a coin around it that now it has points outside of the set, but nothing inside of the set. So where are the boundary points? Well, it's what looks like the boundary of the set in the picture. If I take, for example, the number 3, and I take any coin around 3, it's going to contain things inside the set as well as stuff outside the set. And similarly, the number 1 is going to be a boundary point because, again, if I draw any one coin, it's going to contain things inside the set and things outside the set. So the boundary of the set 1, 3 is equal to just the 2 points 1 and 3. Those are the edge of the interval. And of course, this is contained in the interval 1, 3. And so that implies that the interval 1, 3, the closed interval, right, is a closed set. Okay. And in fact, there's nothing terribly special about 1 and 3. If we took any closed interval, the exact same argument would hold. This is also a closed set. Okay. Now, what if I removed one of the endpoints? Okay, so let's say I took, for example, the half open, half closed interval 1, 3. So it contains 1, but it doesn't contain 3. The boundary of this set has not changed. All right, if we go back up to this picture and I take this square bracket and I turn it into a parenthesis, and I say, oh, well, I take this point 3 and I put a 3 coin down, it still contains points inside the interval and it contains points outside the interval. So the boundary has not changed. However, it is no longer a subset of the interval 1, 3 where we don't include 3, right? Because it's missing the number 3. And so that tells you that the interval 1, 3 with 3 missing is not closed. Okay? Of course, it's not open either, right? For it to be an open set, we would have to have a parenthesis on the left as well. We would have to kick out 1. So here we have our first example, right, of a set which is neither closed, right, nor open. Okay, so this can happen. Okay, another easy example. Let's take the empty set. All right, so what would be the boundary of the empty set? So the boundary of the empty set would be all the points such that when you put a coin around them, they contain points that are not in the empty set. Well, that's pretty easy. And points that are in the empty set. Well, that's impossible. There are no points in the empty set. So the boundary of the empty set is empty, right? There can't be anything in the boundary. But of course, this precisely says that the empty set contains its boundary. Therefore, the empty set, which by the way, we already saw was an open set, is also a closed set. Okay, so and is an open set. So we can have sets which are both open and closed. So they could be neither, or they could be both. Sometimes these are called clopen sets, which is just terrible, just terrible. All right. It's actually the empty set. You might think, well, that's a good place to find it's just too extreme, right? Like you could have weird stuff. But even the set of real numbers, we're going to have this happen, right? So what if I look for the boundary of the real numbers? So now I need real numbers that I can put coins around that contain real numbers. Well, that's easy. And which contain things that are not real numbers. Oh, well, if I'm just looking inside the real numbers, there is nothing that's not a real number. So the boundary of the real numbers is actually, again, the empty set. But the empty set is a subset of the real numbers. So the boundary of R is contained in R, and hence the real numbers is a closed set. And again, we also saw that it was an open set. So we have another clopen set. Okay. It turns out that when you're in any topological space, okay, whatever that means, so you're going to have to choose open sets when you build a topological space. And as soon as you know what your open sets are, you'll also be able to write down your closed sets. And in any topological space, it's actually an assumption that both the empty set and the entire set are going to be clopen sets. Okay, let's do one more example, and then we'll try to write down a different characterization of closed sets. So this last example is I'm going to take some element of the real numbers, and I want to consider the singleton set. All right, so this is a set with just one element, namely this element x. All right, I'd like to know if this is a closed set. So I want to compute the boundary. Well, let's draw this on a number line. There I have my x, and I'm going to put some coin around it. Now this coin necessarily contains things that are not in this set that just contains x. All right, so there you go. I have something which is not equal to x, which is the only point in this set. But it also has x in it, right? Which is in this set. And so, in fact, x is a boundary point. Cool. So I know I have at least one boundary point, namely x. Okay, so x is definitely in the boundary of this set. Well, what if I take something which is not equal to x? Okay, so I'm going to take some y. Well, absolutely, I can put, because of the density of the reals, I know that I can build a y coin that does not contain x. Okay, even if y was really, really close, I could just make that coin really tiny and it will not contain x. Okay, but I've now found a coin, a y coin, that contains elements that are not in x, right? Not in the set, but it doesn't contain any element in the set containing x. Therefore, y is not a boundary point. So x is a boundary point and anything else is not. And so the boundary of this singleton set is precisely the point x itself, all right? Or the set containing x itself. Okay, well this tells me that the set containing just a single point is closed. Okay, so that should give us some good examples to play with. Now, this notion of a closed set containing its boundary, I think, is a very natural one, but it's not the only way to characterize closed sets. So another way is by asking for closed sets to contain the limits of sequences of elements in that set. Okay, so to build up to that, we're going to do another definition here of what are called limit points. And to give us our definition of limit points, we're going to learn about a new type of coin. So if I have some real number a and some positive real number epsilon, we call the set. So here I'm going to take what looks like the beginning of an A coin, except I'm going to stop it at A and not include A. And then I'm going to start it up again at A, but not including A, and go to the end of this A coin of radius epsilon. Okay, so what I'm really doing is I'm taking the A coin of radius epsilon, and I'm removing the point in the middle, the A. Okay, or if I really want to shorten this up, I'll write A minus epsilon, A plus epsilon, sub not equal to A. Okay, but that'll mean the same thing. We're just going to take the A coin of radius epsilon and remove the A in the middle. And we're going to call this set the punctured A coin of radius epsilon. Okay, so now that we have a definition of a punctured A coin, right, which pictorially you're basically saying, oh, there's my A, I'm going to put a hole in here. And there we go. So I have A minus epsilon, A plus epsilon, but we ditch the A in the middle. So that's the puncture wound, right? So if I have some subset of the real numbers, then this A, we're going to call it a limit point of S if every punctured A coin contains an element of S. Okay, and we denote the set of limit points by L of S. Okay, now, what does this notion have to do with limits? Okay, why do we call a limit point something where every punctured A coin contains an element? And let me give you two sort of explanations of why this makes sense. So the first one is just sort of by analogy. Back when you were taking Calculus 1, you looked at things like the limit as x goes to 4 of f of x. And the idea here is that you were looking at values of f of x, right? Looking at values of f of x when x is near 4, but not equal to 4. Okay, this was one of the big ideas, was that when we take a limit, we're not actually letting x equal to 4. All right, and that's because you wanted to be able to deal with things like, okay, there's 4, and maybe I have some function, and it's not even defined at 4, right? And then it goes on. I want to be able to talk about, well, what is the function, what should it have been at this point, even if the function isn't even defined at that point. Okay, so what are we doing here? When we say near 4, we're saying look at a 4 coin, but not equal to 4, we're saying look at a punctured 4 coin. Okay, all right, so that's the first reason why it might be okay to call this a limit. Okay, here's a second reason. Let's say I have my point A, and remember this definition says every punctured A coin. So maybe I put out here a big A coin. Of course, it's going to be punctured. Okay, but it says if I do this A coin, then this coin is going to contain some element of S. Okay, so I don't know where that's going to be. Maybe it's over here. Okay, so this is some element of S. Okay, somebody else comes around and says, well, that coin is too big. I want a smaller coin. Okay, so they do this coin. And again, though, if A is a limit point, there has to be some element of S inside this red A coin. I go, okay, maybe that's over here. Okay, so there's another element of S. Somebody else comes by and says, that coin's still not small enough, right? And they're going to put another coin down here, and I say, well, I guess I need to find some element of S. There you go, found some element of S. Okay. And of course, this can go on ad infinitum. The point is, though, is by finding all these elements of S, I should be able to produce a sequence of points that is converging to A. That's the sense in which we want to think of A as a limit point of the set, right? We can find some sequence of points in S that converge to A. All right, now given this definition, we can write down a new characterization of closed sets. So this is the limit point characterization of closed sets. Okay, so we let S be some subset of R. The set S is closed if and only if it contains all of its limit points. So if and only if L of S is contained in S. Okay, and of course, remember, closed here was saying the boundary of S is contained in S. So we have two different characterizations now of closed sets. One is that S contains all its boundary points, and another that S contains all of its limit points. And these are really fundamentally different. Because, for example, if we take this example we had up above, where we look at the closed interval 1 to 3, I say, well, what are the limit points, right, between 1 and 3? We already knew the boundary points were just the ends, right, the 1 and the 3. Okay, well, let's say I take 1 itself, and I say, okay, is that a limit point? Well, if I take any punctured A coin, so that means I'm going to take this one coin here, but I don't get to include 1 itself, that definitely is containing points in the interval, the stuff to the right. Okay, so 1 is going to be a limit point. And for the same reason, if I write down any punctured 3 coin, Any punctured 3 coin, I'm going to get points that are inside the interval, and so 3 is a limit point. Okay, so everything seems the same so far. So if I take the limit points of 1, 3, I'm certainly containing 1 and 3. Now let's say I take something outside of the interval, say over here to the right. If I put down a coin, you'll notice even if it's punctured, it doesn't matter, I'm still not containing things in the interval 1 to 3. So stuff from outside the interval is not a limit point. Okay, again, this is the same as boundaries. But now let's take something inside the interval. If I take any coin around that interval, even a punctured one, it contains elements inside the interval. So in fact, all of the interior points here are also limit points. So the limit point set for the interval 1, 3 is in fact the entire interval 1, 3. Now again, the interval 1, 3 contains its limit points, and therefore the set is closed. So that's what we liked. So it gives us the same answer, but it's not necessarily talking about the same set of points. The boundary points and the limit points are not going to necessarily be the same thing. All right, so we're going to do a proof of this, and that'll probably be enough for this video. So let's see here. Let's see if we can't prove this. Well, there's two directions. So first, let's assume that S is closed. So assume that S is closed. So by saying it's closed, I mean S is going to contain all of its boundary points. And we want to show that S contains all of its limit points. Okay, fine, let's take a limit point. So assume S is closed and let A be a limit point of S. Well, if A is in S, then we're done. So we might as well assume that A is not in S. So if A is not an element of S, then, well, we know that every A coin contains an element of S. Why? Because A is a limit point. But A also, or this A coin also contains a point not in S, namely A itself. Okay, so then every A coin contains an element of S. Okay, and this is because, right, A is a limit point. All right, that actually says even every punctured A coin contains an element of S. But if that's true, then certainly every A coin contains an element of S. Okay, so it contains an element of S as well as an element not an S, right? An element of the complement, namely A itself. But if every A coin contains an element of S and an element of the complement of S, that means that A is a boundary point. So thus, A is an element of the boundary of S. But we know that the boundary of S is contained in S because S is closed. And therefore, A is an element of S. But that's a contradiction because we assumed A was not an element of S. Okay, so this contradiction shows that A, not an element of S, is a false statement. Therefore, A must be an element of S. So hence, A is an element of S. And because we chose A arbitrarily, we know that the set of limit points is contained in S. Okay, so that's one direction of the proof. The other direction is actually going to proceed very similarly. So now assume that the set of limit points of S is contained in S. Okay? And we want to prove that S is closed, but that means we need to show that every boundary point of S is contained in S. Fine, so let's choose a boundary point. So if B is a boundary point of S, well, then we know that every B coin intersects S and the complement of S. Now, if B is an element of S, we're happy, right? So we might as well assume that B is not an element of S. So if B is not an element of S, Well, we just said every B coin intersects S and S complement. And if B is not an S, then when we say this B coin intersects S, it's not the point B that does so, because B is not an S. So if B is not an S, then there exists a point in every B coin, or even in every punctured B coin, because it's not equal to B, in every punctured B coin that is in S. But this is precisely the definition of being a limit point. Your limit point, all right, if every punctured B coin contains a point which is in S. So thus, B is a limit point of S, but we know that the limit points of S are contained in S, which means that B is an element of S, which contradicts our statement that B was not an element of S. Okay, so now we know that B has to be an S, and so this implies that the boundary of S is contained in S, right? Because we chose B arbitrarily. Okay, so that proves this result. Okay, so what is this result again telling us? We're saying that sets are closed only when they contain their limit points, and these limit points are what happen, right, when you take sequences of elements of S that converge. Okay, so we're going to make this more precise in the next video. We'll write down a theorem that says this, but that's the big idea. All right, we'll see you next time.